Okay, I'm going to run over some notation here, which crops up quite a lot. I'll just write it out, and I'll show you what it means, and I'll justify it. Well, I'll talk about it. See how things go. F of n, where n is some integer, and capital F is some function, equals. I'll just write it out. Sigma d divides n f of d. So we say that f of n equals the sum taken over integers d where d divides n of f of d. Yep, so we'll just have a little example of this. So f of 12, I guess, equals sigma, and quite often you use this notation with the uppercase letter, the uppercase letter here and the lowercase letter here, over d divides 12 of little f of d equals little f of 1, because 1 divides 12, plus f of 2, plus f of 3, plus f of 4, 5 doesn't go into 12 of course, plus f of 6, plus f of 12. Well, there it is. You see this notation quite frequently. You don't actually see it, but it's lying behind lots of quite nice mathematics. So I'm just gonna give a couple of examples. I can write, if I want to write the number of divisors function, tor of n equals number of divisors, I can write it like this. I can write that tor of n equals sigma d divides n of f of d, where in this case f of d equals 1. Do you see that? Do you see how the number of divisors is just the sum over d divides n of 1, because we're counting them? And sigma of n equals, this is almost as clever, d divides n f of d, where in this case f of d equals d. Okay, so that's quite a nice way, and there's a beautiful little piece of reasoning which I'm not going to cover in this screencast, but maybe the next one, where you can take advantage of this nice notation to prove lots of interesting things. Okay, I'm going to stop there.